Okay, the next speaker is, I don't know, Cass. Okay. He's talking about intrinsically correct sorting in Cubical Agda. If you are ready, please start.
Yeah. All right. Yeah, so welcome to my talk, Intrinsically Correct Sorting in Cubical Agda. Joint work with Vikraman and Choudhury, who is also here, Jurriaan and Niels van der Weide. So our story begins with a paper called Sorting with Bialgebras and Distributive Laws by Hinze et al., where they analyzed the recursion behavior of some well-known sorting algorithms from the literature and find out that some pairs of sorting algorithms have a shared business logic that can be extracted in the form of a so-called distributive law. These pairs of algorithms are dual in a way that can be made mathematically precise with the notion of bialgebraic semantics due to Choudhury and Plotkin from their seminal paper Towards the Mathematics of Operational Semantics. And our goal was to intrinsically verify such sorting algorithms. And what do I mean by intrinsic verification? Well, an intrinsically verified program is one where its specification is interwoven with its type, and the proof that it conforms to the specification interwoven with the program. And in order to be able to do intrinsic verification, we needed to work in a dependently typed setting, in our case, Agda. And why Cubical Agda? Well, we needed path types in order to define a multiset type, which we will see later. Our contribution, the contribution of this paper is that we managed to define intrinsically correct version of the sorting algorithms with logics given in terms of a distributive law, and do so in a setting where the correctness of the algorithm follows purely from the correctness of this small non-recursive business logic. And we get from the correctness of one business logic the correctness of two sorting algorithms because of this algorithmic duality. And the key idea is to index the data types involved, so lists and trees for tree-based sorting algorithms by the multisets of their elements. The structure of this talk is as follows. I'll begin with motivating how we can define the. Is this laser? Yeah. Okay. How we can define sorting as an index-preserving map. So basically, a way of formulating the specification of what it is to be a sorting algorithm. Then I give a recap of the paper Hinze et al. To motivate why we have the business logic, why the shared business logic of sorting algorithms is a distributive law, and pinpoint where we will need to intervene for an intrinsically correct version. And then I show how we go about doing that, and also introduce the data type we use for finite multisets in Cubical Agda. All right, we begin with specification of sorting. We're looking at sorting elements of a carrier set A, which is totally ordered. So one inadequate way to express the type of sorting would be as a map from list to list. But of course, there are lots of inhabitants of this type. So we might go a bit further and require that the output is a list of elements A in ascending order. But this, again, doesn't capture sorting fully, of course, because a map that would satisfy the specification, for example, would be the map that constantly returns the empty list. So we need sort of the second part of the specification of sorting, namely that the output should be a permutation of the input. We can rephrase that statement by saying that mapping lists to the multiset of their element is an operation that is invariant under sorting. And this is still an extrinsic way of expressing this property of element preservation. But we can reformulate it once more and phrase it intrinsically, naming that sorting is an index-preserving map if our data types are indexed by a finite multiset of their elements. And so the type we would write for this in Agda would be this: if EI list is element index list, and OEI lists are ordered element index lists. And the index G here in the output is the same as the input, and that is basically element preservation. All right, I begin now of a recap of Hinze et al. 2012, and I'll start with the recap of the categorical semantics of structured recursion, because that's what gives rise to this definition principle of bialgebraic semantics. The relevant categorical semantics is that for recursive data types, can be described by a so-called base functor, which is essentially the data type with the recursion factored out into an extra argument. So the base functor for some common data types here, the natural numbers, would be like the maybe functor. Or for a list of element of type A, it would be 1 corresponding to the nil case, or A times X. And then the recursive data type is reconstructed from this base functor by taking the fixed point of it, which is done by consecutively applying it to itself. And the least fixed point, so in the category of sets, gives us inductive data types, whereas the greatest fixed point of this base functor gives co-inductive types, which are non-necessarily well-founded trees of shape given by the base functor f. So for the co-inductive data type for the list base functor would be lists or streams, so possibly non-terminating lists. Now I continue with bialgebraic semantics. Namely, this is a definition principle that arises in the case where we want to define maps from a recursive data type into a different recursive data type. And I say recursive here and not yet inductive or co-inductive, as you will see shortly, because this basically gives us two different ways we could do it. Namely, we could treat the input data type as inductive, and then we could define such a map by induction, given an algebra for the base functor of the input. Or we could define it co-inductively by giving a co-algebra for the base functor of the output. And a way that gives us both is bialgebraic semantics, where our business logic is now not an algebra or a co-algebra, but a distributive law. And I won't say what that is precisely, but I will illustrate by showing an example of the simplest sorting algorithm defined in Hinze et al., which is the bialgebraic sorting algorithm insertion bubble sort. We have first we have the list base functor, and so we said sorting should go from lists to ordered lists. And so in the original 2012 paper, right, they're verifying it. So they have an ordered list base functor, but this is just an alias for the normal list functor. And the shared business logic of insertion sort and bubble sort is given by this so-called distributive law. Again, I won't go into the details of why this corresponds to these algorithms, but suffice it to be said that this is logic, and then the recursion is added back in by using folds and unfolds. Right, so this is what we're starting out with, and we want to define an intrinsically correct variant of a sorting algorithm that should also have a business logic of this form. I will pinpoint now why the type here is not sufficiently expressive to guarantee that sorting is correct. Obviously, one error we could make is not correct in inversion. So here, B is smaller than A, but nothing in the type prevents me from just leaving those in order. Another mistake I could make is I could discard elements, or I could duplicate one of the elements, and this would violate element preservation. And then a third issue, and this I've sort of swept under the rug until now by talking about the recursive data types, which are only really a notion in a category where the carriers of inductive and co-inductive data types coincide. And that is that bialgebraic semantics necessarily makes use of unfolds. And an unfold for any arbitrary co-algebra could produce potentially infinite data. But we know that sorting gets a finite list as input and therefore should return a finite list as output. So somehow we need to have unfold operations that get co-algebras that are known to terminate. All right, so now I will go about the intrinsically correct version of the types in question. And as we just saw, the business logic is at the level of base functors. So that means that we need to encode all the properties we're interested in, so element and orderedness also at the level of the base functor. And I will also show how indexing by the finite multiset of elements guarantees that unfolds of the co-algebras in questions will always terminate. So now I begin with the data type that we use for finite multisets. This is quite relevant to the rest of the formalization and also the reason why we're using Cubical Agda. Namely, this is so-called quotient inductive types, where in addition to the normal point constructors, so here nil and cons, we have path constructors, which allow us to construct the equalities of this type. And so this data type models basically a quotient type of lists up to permutations of their elements. And this com constructor, which at first sight looks to allow only swapping elements at the head of a list, but composition and congruence allows us to identify all lists that are syntactic permutations. Yeah. And so on the next slide, I will show how we will index, how we'll define base functors for indexed lists and ordered element indexed list. And so I introduce these synonyms to disambiguate the nil and cons constructors of this finite multiset type from those of the base functors, since Agda normally allows constructor overloading. Okay, so I have rewritten here the list base functor that we saw earlier, but left some suggestive blanks, which will be filled in with the index information akin to the Conor McBride's ornaments idea, a data type and sort of adding information to it. And the information we add is this finite multiset index. So it gets added as an index parameter at the type level, and then we see the empty base case that's going to be indexed by the empty multiset. And in the cons case, we add the element const onto the list, onto the finite multiset index of the recursive position. So this is how we encode element indexing at the level of base functors. We can encode orderedness for the ordered list base functors by simply requiring an extra argument, which is that the element to be const onto a list be smaller than all the elements in the multiset index of the recursive position. And that would give us lists if you iterate that. All right. So now we have the base functors in place. The third problem that I pointed out in the recap is how do we ensure that co-algebras for the base functor are actually well-founded, so they will only produce finite output if they are unfolded. And I will show this on the basis of the L base functor, since the orderedness is not relevant, only the element indexing is relevant for this termination argument. Yeah, so the type of the unfold operation is the following. We have a higher order function that gets a co-algebra for the L base functor as an argument and returns a map from a seed type to a list. And this works by a repeated iteration of this co-algebra, applying it to the intermediate seed values that are produced. The way that termination that will be showed is by using the fact that this co-algebra is also an index preservation. So the index of the seed value and the value of the L base functor that is produced are going to be equal. And so what I'm using here is Agda's with abstraction. What this allows is for a given function, I can refine earlier arguments to the function definition by pattern matching on an application. So I apply grow to the seed value, and then I know that if I'm outputting the empty list, because of element indexing, I know that the element index of my original seed must have been the empty multiset. And if I output the cons case, so an element to be output and a new seed, which is indexed by multiset G prime, then the original multiset index G must have been equal to X multiset cons this G prime, so the new multiset index. And this is what I get by index preservation. And this means that the multiset index acts as a termination argument. So you can think about this index seed like a seed for such a co-algebra being indexed by the finite multisets of all elements that will eventually be output by iterating this co-algebra. And with every step, if I output an element, then that index decreases. So by that argument, we know that unfold of any L co-algebra will produce only finite output. So there's a small problem. So if I just write this definition like this in Agda, it won't accept it as terminating. And this is because if you do syntactic termination checking based on these redundant patterns, these dot patterns as they're called, in Cubical Agda, then you can prove falsity. This is because of path constructors. So you can't just do this for any higher inductive type. But we can easily remedy that by defining this map by using well-founded induction of finite multiset. And this length is just defined by using the universal property of the finite multiset as a free commutative monoid. So there's an implementation detail, and we also mentioned some more details in the paper which are relevant to working with higher inductive types. All right, so now with the data types in place, we can revisit the original the distributive law, but now in the index setting where we have intrinsically verified it. As you can see, at the type level, we know that we have index preservation. And we had added this additional argument to the cons constructor of O, where we need to provide a proof that the element to be cons is smaller. So you can see we provide that as an extra argument. And then in the final line, you can see there's this subst thing. And this is because we've corrected an inversion, but that means that out of the box, the multiset index is going to have the elements swapped. So the order in the elements has been changed. So we need to substitute along the path constructor com, which allows exchanging the elements, to convince Agda that the finite multiset index has remained the same up to this path equality. So this is another technical detail. You might wonder, okay, what does the term like an index data type, a data type indexed by a higher inductive type, substituted along one of the path constructors of this higher inductive type, what does it evaluate to? And this evaluates to a sort of semi-stuck term, or a normal form, basically. The way that data types indexed by higher inductive types are implemented is due to Cavallo and Harper. Yeah, you get these normal forms, which are of the form transp something. So you can necessarily do something with that, but then you can just forget the index information and map this back to a normal list. And by doing that, you will just get an algorithm. All right. Now to conclude. So what were we able to do? Well, by indexing by this finite multiset, we achieved three things in one go. We encoded the element preservation property. We encoded orderedness by using the all predicate transformer. And this multiset index also acted as a termination measure for the unfolds of coalgebras for the ordered list base functor. And the intrinsically correct algorithms we get as folds or unfolds are correct solely by virtue of the intrinsic correctness of the distributive law. So we have basically localized the proof obligations to a non-recursive thing that the algorithm does, which could be argued to be its essence. For more algorithms, so we also verified the other algorithms from the original Hinze 2012 paper, which are quick/tree sort and bottom-up/top-down heap sort. This is basically routine once you have figured out how to do things in this index setting. And we also outline a categorical semantics of what we're doing. Namely, we work in the slice category set over multisets, finite multisets. And for those, I refer to the paper. Finally, future work. So this is something I'm actively looking into as well. Is I'm interested in conditions under which we have these coalgebras in an index setting, which are all well-founded. Another question would be, are there more algorithms, more interesting algorithms whose business logic can be expressed at the level of a distributive law that we could verify in a similar manner? All right, that was my talk.
Time for questions.
In the final slide with the code, where you describe the substitution thing, is there any reason to define the tourist to not preserve the index? I mean, instead of defining ER list G, you use list A. Is it? Yeah.
Yeah, I mean, basically, throwing away the index is how you get it to look like something recognizable. Like, if you can keep the index as long as you're working in this index setting, but afterwards, if you want to continue using it like in the rest of your program, then you have to forget about the index. So that's the only reason why you would do that.
My question would be, would you think that it's possible to also verify the complexity of the sorting algorithms in this setting intrinsically?
That's a good question. So basically this multiset index, right, it kind of acts as a step counter in a way. So in the original paper by Hinze et al., they do note about the complexity that, like, for these, like, the naive sorting algorithms defined in this way, you get like the quadratic complexity, and there's kind of a sort of hand wave reasoning, like it's not verified, but I think it might be possible. Basically, structured recursion like limits the way in which you can define things, right? So in that sense, it might be possible to do that. I'm not aware of a framework where you can do that exactly. I know there's some work about like about using step indexing, and so, but I think those complexity proofs, they're usually done in some framework where you sort of have these you do the step indexing outside of the algorithm, sort of in your meta language. Whereas here, this multiset index kind of, it exists in our object language, right? We're dealing with it in the code of the program itself. So I'm not sure exactly how it would translate, but it might be possible that you could use this also for the complexity. So then you would do three things in one go. Complexity and termination, they would go hand in hand. But yeah, that's a good suggestion. That could be possible.
Before the question, could the next speaker come up and start saying the
It's not clear to me, what do you use the truncation argument in the multiset definition? It never shows up in the slide after. Could you remove it, or?
Okay, so why are we truncating? We can't remove it because this is defined by eliminating from the finite multiset, and you use the fact that it is a homotopy set. You eliminate into the homotopy set of propositions, and so I think it's necessary for that definition, and also for the length that we also defined by the universal property. One thing, yeah.
The length you could define it directly with a fixed point, or?
Yeah, the length you could define just by pattern matching and recursion, but the predicate, that's the one where you really need to use the universal property, and there I think you can't do it. So yeah.
We can take one more question. Any other question? Then let's thank the speaker again.